Problem 47 tries to give us intuition about an important topic called independence of events. And this is a topic that's covered extensively later in the book. But I suppose in this problem, the author tries to give us some intuition for what this concept means. So for part A of the problem, the algebraic definition of independence is given, and the definition is two events A and B are independent if the probability of their intersection is the product of the probabilities. And so we need to give an example of two events that are independent. So consider flipping two coins. What is our sample space? So we could have heads, heads, we could have tails, heads, we could have heads, tails, we could have tails, tails. So we have four outcomes in our sample space, each of them equally likely. Let's let A be the event that the first flip is heads, and B be the event that the second flip is heads. So probability of A then is the first flip is heads. Well, there are two outcomes, namely the first and the third, where the first flip is heads. So we get 2 out of 4, which is a half. Probability of B is that the second flip is heads. So this is also 2 out of 4, which is a half. Now the probability of A intersect B is the event where both flips are heads, and so that's 1 out of 4. So we see that if we take the probability of A and multiply it by the probability of B, we get exactly the probability of the intersection. And by the algebraic definition of independence given to us, these two events are independent. Now let's consider part B. So part B uses a different intuition for independence. There are numerous ways to think about the concept of independence. So part B uses a different concept tied to independence known as conditional probability. Something that's covered in the second chapter of the book. So it uses the topic of conditional probability. So what does this mean? Under this framework, we can think of independence in the following way. Two events are independent if knowledge of the occurrence of one event does not change the likelihood of occurrence of the other event. The way we notate this is the following. We say, if you tell me that some event has occurred, let's say event A1 has occurred, the likelihood of another event having occurred does not change. So the right-hand side, I had some prior likelihood of event B1 occurring, then knowledge of A1 having occurred does not change the belief of event B1 occurring. So this left-hand side here is called conditional probability. We're conditioning on the fact that the event A1 has occurred. And this has a formula, and it's equal to the probability of the intersection of the two events over the probability of the event to the right side of the bar. So this here is this concept of independence viewed under the lens of conditional probability. So we need this to hold. We need this equality here to hold. So then what is the condition? So in problem B, we're dealing with these two rectangles. These rectangles A and B. And the probability of the dart that's thrown in the problem landing in any of these rectangles is equal to the area of those rectangles. So the probability of B1 is equal to the area of B1, the probability of A1 is equal to the area of the rectangle A, etc. And so for these two things, for these two expressions to be equal, what is the condition? The condition is that the ratio of the intersection the ratio of the area of the intersection of A and B to the area of A equals the area of B. Since the probability of B here, this expression here is the area of B. This expression is the area of A, and this is the area of the intersection. And so we're saying the ratio of the area of the intersection to the area of A has to equal to the area of B. And when that happens, these two expressions are equal, and we have independence between events A1 and B1, between the event of the dart landing in one rectangle versus it landing in the other rectangle. Now, let's come up with a simple example where independence breaks because this condition is false. So let's say A and B are the same rectangle. So if A and B are the same rectangle, then the probability of A1 intersect B1 is just the probability of A1, since A1 and B, since A and B are the same rectangle, and so probability of A1 over probability of A1 equals 1. But this 1, so in other words, this probability of B1 given A1, this expression here, does not equal the probability of B1. Why? Because we're given in the problem that neither of these rectangles has an area of 1. So we know that this expression here does not equal to 1, whereas this expression does. It does because A and B are the same rectangle. So this probability of B1 intersect A1 is just the probability of A1, and so this ratio equals to 1. So the probability of B1 given A1 equals to 1, whereas the area of this rectangle B does not equal to 1. And so so these two expressions here are not the same, and independence does not hold. Again, it's okay if you don't understand this problem. Again, this uses the lens of independence viewed from this concept of conditional probability, which is explored later in the book. So moving on, part C says, let's assume we have two independent events A and B that are so they're independent, and we need to show that the probability of their union is 1 minus the product of the probabilities of their complements. So this is what we need to show. And so this is just a case of doing some algebra, and we could say probability of A union B equals probability of A plus probability of B minus the probability of the intersection. So this equals probability of A plus probability of B minus, now we're going to use the independence, the algebraic definition of independence, so this becomes the product of the two probabilities. At this point, we can factor out the probability of A and get 1 minus probability of B plus probability of B, and we can rewrite the last probability of B actually what we can do is we can rewrite 1 minus the probability of B as the probability of B complement, and we can rewrite this as probability of A times the probability of B complement plus 1 minus probability of B complement. which now we can rewrite as 1 plus the probability of B complement multiplied by probability of A minus 1. Probably so you can expand this out if you want, and you'll see that these two lines are the same. And this becomes 1 minus the probability of B complement, probability of A complement. And this is because we can rewrite probability of A minus 1 as we can factor out a minus sign, and this becomes 1 minus probability of A, which is the probability of A complement. And so we have the desired result. Just by doing algebra, the important step is this. So this is where the assumption of independence is used. So again, we have a problem consisting of 3 parts. In the first part of the problem explores the concept of independence by looking at the algebraic definition. The second part explores the concept of independence by looking at it from the lens of this conditional probability concept. And the third part just utilizes the algebraic definition of independence to prove some property of probabilities. Again, don't worry if you don't understand anything about this problem. The concept of independence will be explored later on.